Okay, I think we can get started. Today we will talk about the controllable simultaneous synthesizer for image and annotation generation for image segmentation task. The innovations of this paper include three aspects. Firstly, it proposes approach for synthesized images and the corresponding segmentation masks simultaneously. Secondly, the proposed approach can control the style and the content simultaneously, and this can give us more data diversity. Thirdly, it reuses the feature representations in the generation process for semantic segmentation, and this gives us very good segmentation performance. Also, the empirical results shows that it can achieve really high performance. Yeah, the limitation of this paper is that there is seems to be no quantitative measure of the image quality. Okay, about the intuitions. Firstly, the adaptive instant normalization generated with the Walsh net module can give a pretty good representation. This representation can be used by the ensemble multi-layer perceptron segmentation module, and let the model to be trained with a very small number of labeled data. Secondly, if we directly train the model ensemble multi-layer perceptron for a small number of real city images, I personally don't believe it is possible to achieve very good performance, since we may not have a good representation. And this paper is published in MICCAI 2022. Okay, first about the system architecture. Here is a comparison of this proposed approach and the existing approaches. Figure 8 is is approach. Sometimes people call it vector-to-image models. The key idea is a generative model is used to generate a synthesized city image from a noise vector, and for this synthesized image, we manually label some of them to get a segmentation masks, and these segmentation masks and the synthesized city images will be used to train a segmentation synthesis module. In figure A, it shows another approach we call it mask-to-image modules. Here is we have a manually adjusted masks and the corresponding images, and we use these pairs to train a GAN. This GAN can convert this mask to a corresponding image. In figure C, it shows another approach, vector to mask to image model, as is indicated by the name. A noise vector is first converted by a generative model to get a synthesized mask, and this synthesized mask is then used to generate a corresponding image. In figure D, the proposed approach is presented here. And you can see there's multiple procedures. First thing is a real city image is first used to get a hue value map. And this hue map will be combined with a reference city image. And the combination will be fed to a multiple adaptive instance normalization GAN. And this normalization GAN will then generate a synthesized city image. And this is about the image generation part. The second part is about the segmentation mask generation. So the key is we use the representation from the adaptive instance normalization GAN as an input to a segmentation model, and this segmentation model will generate a segmentation mask from the learn the representation from adaptive instant normalization GAN. Of course, we need some labeled data in the segmentation mask training process, and these labeled data are associated with the synthesized city images. Okay, let's first talk about the whole procedure actually is not trained end-to-end. It's achieved by a multi-stage training. Basically, we train each part separately in a sequential way. First, let's talk about how to generate this the hue map. So here is the training process. Then during training, a city image is fed to a convolutional neural network. We get this output feature map. You can see it has the same spatial resolution as the original image, but it has different channels, and the number of channels correspond to the number of the object classes in this image. And when you do the argmax over these different channels, then we get the segmentation mask. For this segmentation mask, we will do some later process for it. Let's go back to this image again, input image. And this input image now, instead of apart from feeding into this convolutional neural network, it's also fed to algorithm, and this algorithm will give us a superpixel image S. It has the same resolution as the input image, and this superpixel image will be combined with the segmentation result we obtained from the convolutional neural network to get a refined segmentation result. This refined segmentation result can be treated as the ground truth, and we will use this refined segmentation mask with the output feature map to get a cross entropy loss, and this cross entropy loss will be used to train the whole model. So once the model is trained, we just use the upper half of this flow chart. We don't do the calculation anymore. What we do is, for example, at inference, for every given image, we first generate a hue map. Generate the superpixel image, and then we get the feature map from convolutional neural network. We get the segmentation mask, and we get the refined segmentation mask. And this refined segmentation mask will be used to get a HU map where this mean HU assignment approach. And this whole process will need to be trained before we train the data on process modules. Okay, so suppose we have this HQ map generated. So what about next? So the next part is about this synthesized image generation. To generate this image, we need another reference CT image. For these two images, the reference CT image can give us the style information of this CT image, and this HQ map can give us the content information about the image we want to generate. When we combine these two, we get the final image. So here is how it works. First, for each of these reference image and the hue map image, an encoder will be used to generate a feature map for each of them. And then the style feature map from the reference image will be combined with the content feature map from the hue map and then the combination will be fed to this adaptive instant normalization, and we let it go through the decoder part, and then we get this synthesized image in the end. Also during the calculation at each layer of the decoder, the style features is also fed to the different layers, so that at each layer it can combine first the style feature. You can treat it as a residual connection, and then it can generate the final goal is to generate synthesized image. Okay, so when you get this synthesized image, we need to formulate this loss for training the model. So here's how we can do it. First thing is this reference city image and this synthesized image will be, both of them will be fed to this VGG feature extractor. This feature extractor is fixed and it can give us the representation for each of these two images, and their representations will be used to form a style matching loss. Ideally, we expect their feature to be close to each other since they have the same style. Second part is about the content loss. The content loss, we will combine the synthesized image with the hue map image, and we get the content matching loss. Another thing is about the discrimination loss. Yeah, just as we did in this GAN training, we need to tell whether this is a synthesized image or real image. So what's the image synthesization model? Basically synthesized model is a trend that we can then consider the training of the mask generation model. To do that, we need first to get some labels for these synthesized city images. So in this paper, the authors used 30 such labels for the synthesized images. And those paired synthesized images and their corresponding labels will be used to train this segmentation mask generation model. But instead of directly using the synthesized image, in this paper, actually the representation learned for this synthesized image in the adaptive instance normalization GAN is actually used as input of the segmentation mask generation model. Yeah, so this segmentation mask generation model is takes the representation from the adaptive instance normalization GAN as input and gives the segmentation mask as the output. And this segmentation mask will be combined with the manually labeled segmentation mask to formulate the segmentation loss. And this segmentation loss will be used to train the whole system. Once the whole system is trained, we can use this segmentation mask model to generate this segmentation mask. Then we get the first the synthesized city images and also the synthesized segmentation mask. We can then have a synthesized image segmentation data set. So here is a illustration of the segmentation mask segmentation performance. If we look at the figures, the plot in the figure D, we can see it achieves pretty good segmentation performance. Okay, so suppose we use the synthesis data to train a segmentation model and evaluate the segmentation model on some other data set. So what will be the performance? So here is a plot shows the behavior of this model. For example, if you look at the figure A on column 1, you can see that for their data set, we need a very small number for images, synthesized images, and the corresponding segmentation masks to train the model. And this the trained model can then achieve pretty high segmentation performance on other data set. For example, here it achieves more than 0.9 dice score coefficient here. Dice score here, yeah. Okay, that's all. Thank you.